Okay, off you go.
Okay. Oh, hold up. Okay, so guys, today I will be doing a short demo about the PVS. PVS is the Theorem Prover, and right now I'm SSH to the school's computer, the Prism computer, and you can launch the PVS using command line PVS and type the file name. Here I'll do the PVS demo and then launch the PVS from command line.
I will also make the file available to you for your information too.
Right. So the file will be available later in the course website. So PVS, just like Isabel and any other things, is Theorem Prover. It's a specification tool for specifying like a function or it's mathematical. Like it's specifying like mathematical theorems, and then it's capable of proving them like manually or like automatically. To prove them, to prove that the specification is correct. So for the first demo, I'll do like a very simple one. It's a very simple like equation, mathematical equation. 4 plus 3 is 7. So here I'll use PVS to prove that this equation is true. So I'll do Control C and P to here. So the thing below this line, so here below this dotted line is the goal, the thing that we want to prove.
Just mention something. So if you choose a Theorem Prover, for example, in your case, what your compiler will generate is a file like this, which you're going to make available. But the actual interaction with the tool, you'll be another story. Either you will be maybe me and the TA will try to run according to your instruction to try to prove the output file, or maybe you'll consult with you how to prove it. Simple example.
Okay, so here is the PVS is asking me the rule for this one. So I will just do observe. Just the PVS will run the mathematical, just calculate, and then the proof is done, and that's it. That's the first demo. Very simple. You just do observe, and
remember one of the basic things we should really get to work in order to pass would be some arithmetic. There you go.
Yeah. Basic math. And then the demo 2 is simple logic. So okay, I'll go to proof.
This is the proof.
What's that?
This is the proof.
This thing is the proof. Like how do you type to prove the equation?
Okay. So it's generated
now? No, it's not generated.
So we come up with it ourselves, but
right.
PVS proves it for us.
No. You come up with the thing, like with this, and then you prove it yourselves. So it's just like 1090, just like 1090.
proof assistant.
Yeah.
Simple things they can prove, but typically you have to be
right.
experts
doing the proof.
Yeah, you got to be an expert knowing all the inference rule they can use. And then I would say in simple, they claim in many cases that may be non-trivial. If you simply, he will show you something
right.
grind. If you simply hit your grind, you can discharge it. But in many cases, you cannot. In that case, you have to
prove it yourself.
Well, I was reading about it, and they were saying that in like a software engineering thing, they were saying that really the experts are you can put them all in one bus. That's how many people who are experts because you have to like pick like the right set of assumptions. Anything too strong or problematic will cause like any other issue.
Yeah, remember we're dealing with an inference, like a proof system. If you somehow introduce some unnecessary or unreasonable axioms, they can just break.
Yeah.
So be careful what you generate for the theorem proof. Right. But afterwards, it's not a theorem proof course, so we will not be so picky when you conclude the C unless it's too ridiculous.
Okay.
Other questions? Go ahead.
So our task is to create a compiler that follow this.
What you will create is simply just a specification file, not the proof itself. You don't generate a proof.
Right.
Maybe what you can try, for example, you can say I can invoke the prover maybe with a default command like a grind to try. If it succeeds, your compiler will say, okay, here's a proof. If it doesn't succeed, you will tell the user, if it doesn't succeed, you should really load the file as generated by the compiler and then try to prove it. That could be one option. But we'll talk about this individually when I meet with the team.
these files have like specific syntaxes.
Yes,
Right.
exactly.
So
So
our
the,
compiler is just taking the syntax that you look at this, we decide if we like it, create the syntax based off.
no, your compiler takes the syntax. If your compiler takes the syntax of your programming language, you own, and then it compiles that into a file that conforms to the syntax of the very beginning.
Is this a programming language that already exists, or we can also create our own?
Which one? You mean this one?
For our project.
We're creating, so like, we look at this, and if we like the specification language, then we build it, like, you know when you make your syntax? You make your syntax, and then the compiler turns it into
Okay.
this.
If you don't mind, I take over very quickly.
Yeah, that's.
Okay, I want to make sure you hear this part, right? You can, okay, if you don't mind. Yeah, I'll switch back. Sorry for interruption, okay? Okay, very quick, okay? But, you know, it's good that you have questions, but just in case, right? Let's say, in case you choose PVS, in case, or something similar. The PVS itself has a specification language. And as I said last time briefly, the best way for you to understand about this language here is not to study its grammar. No, don't do it. Okay? What you should do is go to their website there, or simply Google for each of the tool. They got many users who's contributing about working example. Study them and then get an idea what you can do. And then once you see, let's say you've seen so many specification feature for the PVS or any Theorem Prover tool. Don't be too ambitious. Maybe choose maybe the core ones that you believe is going to help you. And then work backwards based on these features that PVS can support. So now what should my programming language look like in order to be supported by these constructs, right? And then what you'll go is you'll say, now I'm going to think about if I got my input program over here, and this guy here will be your .g4 file, right? Your Antler specification file. And then when that's passed to your compiler, and then the compiler is going to generate something that can be fit into PVS. So you can think about this file here, .pvs, is what Shangru just demonstrating right now. Okay? Depending on which Theorem Prover you choose. Any question? Go ahead.
I have missed something. So for PBS to work, we need to write the proofs. It's complicated, right?
Okay, let me clarify this. Okay, let me clarify. First of all, up to here we are fine. Okay, your compiler is going to generate something I put in orange. You can think about this is some valid input for the prover. Well, I'll just say prover for now. Okay, let me finish this and I'll take your question. Right? So it's going to be valid input for the prover. If you can get this part done and also you informally justify why you believe your generated output is actually correct. Well, when I say correct means the transformation is actually correct. Why? It is semantics preserving. If you can justify that, I'll be happy enough. Okay, what goes afterwards? It goes like this. You will provide 10 examples, for example, right? Provide 10 working examples there, and then tell us exactly, okay, let's say for example, I'll say example1.pvs altogether to example10.pvs. Okay? Only for these examples, you have to say, this is how you load it to PVS, and this is how you can prove it. Okay? Those will be manual. And me and my team will choose some example to try them out. Okay? That'll be it. Okay? But if you really get stuck in proving the generated example, you can speak to me. Okay? I wouldn't be too harsh on that part. I think what's really important for this course is get this part done, and then have some reasonable justification why the generation process is justifiable. Then that'll be fine. Okay?
So we're not generating other code at the end, right?
Say that again?
Can I convert? So you said we were going to make an input for the DBS. But
Yes.
we're not generating any point another code that actually runs.
You don't generate any, no. You only generate input for whatever verification tool you choose. Yeah, that's all you do. In case it's a model checker, you only generate input from model checker. So I will show you some example from model checker maybe on Monday. So just to be balanced. Raymond.
So for example, like one simple example for the valid input for the prover would be the file that you just showed us, which said 3.
Exactly. For example, I'll give complete example. Let's say for your particular program, right? For the base case, let's say over here you simply say, let's say I declare variable x equals 3, variable y equals 4, variable z equals 7,
And then let's say if you support a keyword called assert, and then you would say x plus y equals z. If that's one of the example. What you would do is you're going to generate some PVS file that looks like just like what he demonstrated as the first one. Okay? However, be careful. Remember I said the 10 example should really give me in the TA a very reasonable approximation of how capable your compiler is. I wouldn't mind if you only got 1 or 2 examples that are kind of basic, right? But you should really get some advanced one. You want to show off how capable your compiler is. Is it clear? Okay. Yeah, get some clarification today, but we can keep clarifying, right? You still got time. But who? You, in order for the compiler to work, you got to design a programming language. Yeah, the input programming language. Question? Well, you're fine. You're fine. Okay. Yeah.
So are we meant to all these stages of compilation?
Say it again. I don't quite catch you.
Meant to all these stages of compilation?
You get the implement, yes. So the compiler over here, you can think about once you take the grammar of the G4 file for Antler, it's going to generate a parser, right? Will be some Java classes. And then you're going to also take other Java classes that you define, and all together will be a compiler. So what's really missing there is how can you say, if I give this thing here and then it's turned into a parse tree, how can I eventually turn that into an input for PVS? That's your job, right?
Okay.
Mm-hmm.
So the target is whatever.
Whatever, yeah, that's why I gave you choice, right? Okay. So when you guys do research about verification tool, so feel free to suggest anything I didn't list. I'll be quite open to it, but speak to me first, okay? Okay, come on, continue. All right.
Back to the terminal.
Okay, we'll just let me do a little bit more. We haven't seen any interaction with Prover just yet. So what we just saw here was the assert, which is automatic. That's preview. That's easy.
Yeah. So for the previous example, it's pretty trivial. For this one, we have to prove that like for z is larger or equal to 1, and yeah, so it's basically right here. So for this and that to be true if and only if z is equal to 1.
Okay, let's just put it to you. You can see over here, conjecture here. We say that given that z larger than or equal to 1, and also z less than or equal to 1, if and only if z equal to 1, right? They're equivalent.
So we have
Question?
like let's say we pick Java as our language. We have to like
What do you mean pick Java as your language?
like defining that Java the syntax.
You're going to design your own language. Although your language might look like Java,
Okay.
that's okay.
Okay. So we have to convert our own language to like to preserve the semantics of conjecture.
Exactly.
Okay.
Yeah. You want to convert whatever programming construct you have in an input into something that's specified in PVS, for example, and then make it semantically equivalent.
Okay. That eventually be known to put conjecture there.
Yeah.
Okay.
Yeah, but of course, they might have different keywords in the specification, right?
Yeah.
You have to.
Yeah.
Okay. Yeah. Go ahead.
Okay. So to prove this, I'll first do a thing called prop. This will get rid of the and if only if. So right here we have like this thing. So this thing means that to prove z is equal to 1, it is sufficient to prove that like the thing above. Like that, we have this on our hands. The goal is to prove z is equal to 1.
Yeah, think about these two are the antecedents, and that's the consequence.
Right.
That's another way to think.
And it's pretty clear, so we can do assert. Let's do, yeah, the first one is proved automatically, and the second is the same thing. To prove, yeah, the below, easy, assert. Third one, do the same thing, and this is the second demo. It's a really simple logic thing.
Okay. So why don't you go directly to the last one?
To the last one?
You have to interact with by proving by induction. How about you do that one?
Okay, sure. I can show this for grant.
Okay,
I can grant this. Okay. So there is a command in PVS called grant. It will try to automatically prove the thing for you. Like it will smash like all the rules like on PVS to prove this. So I'll try here, and then voila, it proves automatically for you.
I suspect, I imagine, for the basic predicate you want to assert from your source programming language, they can be just grunt.
Right.
But depending on the theorem prover, they might call something different from grunt.
Yeah.
They are similar, something similar.
Yeah. So okay, so this will just grunt and it will grunt away. And for the last demo, we have a function. We have a function called square. So square is a function that takes n is a natural number as an input and returns a natural number. So it's trying to square n. And so the square is defined at n times n. Okay.
And question for you guys, if you want to prove by induction on the set of natural numbers, how would you do it? What would be the base case?
Zero is not a natural number.
Zero.
Oh, you know what? Depending on the definition.
Yeah.
Math
Yeah.
is not, but in CS people define it.
Interesting.
Yeah.
We are in lit CS.
Yeah.
Good man. Yeah, that's fine. Yeah.
Good.
Okay, let's assume natural number means from 0 and above, right? But now if you want to prove by induction, you would say 0 will be the base case, right? That's exactly what he's going to do.
Yeah, so we can also write the function in FO. It will look pretty much like this. Notice there is a tab correct restriction, like precondition, because we specified the input to be natural numbers, so that in FO I don't think we have natural numbers.
It actually does support natural numbers. It does have
They do?
It's called natural. It's actually called natural. Yeah.
Okay, I would just do. Okay, I'll just do integer and then n larger or equal to 0 as a precondition. And so in FO is a implementation. Yeah, implementation. PBS is a specification. It's specifying the function square. So FO is implementing the function square. Okay, so in FO we have ensure as a postcondition such that for like every square, like for every n, the square of n is not decreasing, which means that n squared has to be strictly larger or equal to n. And in PVS, we can write that as a theorem.
So now in this case, let me.
Okay.
So you recorded. You can think about this case over here. Okay, just thinking this way. Assuming that your input language looks something like this, maybe. Okay, so your input language actually support precondition require. Doesn't have to be called require. Maybe pre or post, right? Depending on your syntax. You have some precondition. You have some implementation. You also have maybe a post condition, right? So it could be formulated into the PVS specification like this for all, depending on your translation pattern. So feel free to make some assumption about what your source input language can support and document it properly. Okay? Okay, go ahead. Okay, maybe show the final step just to interact.
Right.
Yeah. Yeah, go ahead.
So in order to do the square root,
Mhm.
the square function,
Yeah.
we have to somehow implement that in our own language.
In that way, I would say, okay, how about this? Let me just illustrate this. Again, so that's why, okay. Or you can think in this way, okay. Because, let's say from the PVS side, okay, because you know, they have a syntax goes like this. You can say square, okay. Again, I got very short-term memory, so I gotta,
Parentheses n
oh, sure,
colon nats.
good.
Parentheses colon nats.
Parentheses
Yeah, no nats. It's just nats. Yeah.
equals, okay. Okay, n times n. Good. If you know there's a particular pattern that you can write in a PVS for a function, so that would mean maybe you should really support in your source language a function, right? So now, so this would tell you that maybe that means in your source language, maybe something dot Raymond, for example. You can make the extension whatever you like, and now here, basically all you need over here is basically, maybe you want to say, I have a keyword called fun, right? And then exactly how you define the syntax, it could be, for example, you always put a return type first. You can say net. It doesn't really mean you cannot support a type called net, right? So net, and then you can call it square over here, and then you have whatever input over here, and then you can say, if you want to use a Java syntax, the old style. This old style say do and then OD. I forgot which language it was. Was it Pascal? Oh, Bash. Yeah, feel free to do things like this. That's why you want to practice, right? Whatever syntax you prefer. And then here you can say, either you can say return if you wish, or you can say result is assigned to, right? Basically, think about what PVS or whatever Theorem Prover can do, first of all. And then think about what I might support so that they can be verified. Mm-hmm.
Pascal is like much older. I thought based off of Pascal.
True. Block syntax. True. And I remember my compiler project for this course back in 2006.
You took this course here at York?
I took this course at York. You know what? The funny thing is, the last time they offered this course was back then. So the last time people took it I was one of them. And yeah, it's actually quite hilarious. I wouldn't enjoy that particular instance because it was a PhD student teaching it. And to be honest with you, there was not a single class I didn't fall asleep. I really tried. I just couldn't stand myself. Yeah. Anyway.
Did you give him calculating with like breaking the clock?
I think it's a paper-based. Yeah, I'm pretty sure I said something bad about him. Yeah. Yeah, not in an emotional way, of course, Yeah. All right, anyway, hopefully that wouldn't happen in this course, I hope. Okay, let's see what happened. But back then, my project was to translate from Pascal into C code. That was the project. Yeah, okay. Anyway, okay, you want to continue? Okay, finish that?
Go back to the terminal.
Yes.
Yeah.
Again, this particular demo just to give you some idea, so you have some idea.
Right. So here we are proving the post condition. Okay, square non-decreasing, like 4. Okay, I'll do. Right. Okay, so here we go. So for this case, the auto prover, the grind will not work. So if I do grind, it just gave you some non-proving thing.
So maybe for your compiler, you will try to invoke maybe something in the grind. Maybe you try. And then if the grind didn't simply tell you that it wouldn't work, then you can just return back to the user, it wouldn't be proof automatically. You have to do that. W now.
Yeah. So I will undo the step. Go back to this. And then I'll do induct, mathematical induction on n. So there are two cases. The first case is that n is equal to 0 because we're using natural numbers. And so the PVS doesn't know the definition of square. And then we have to expand the square so that the PVS know like to go to the definition of square, replace n as 0, and then we can do assert ERT, just proves. And this is the inductive step. So I will do skip to get rid of the for all, skip to get rid of the for all, and then.
Don't worry too much about the specific command.
Right.
There's one, for example, there's one command in there that can get rid of the multiplication.
Yeah. Okay. Then same thing. I will do expand PAND, expand the square, so that did I type it wrong? Yeah. Expand as QUARE. Get rid of the square, and then I can just do assert, so that PVS will calculate the thing automatically. Question?
Professor, but this part is like the proving.
That's out of your context, exactly. So.
Show you that what we provided is enough.
Yeah, so what you provided, let me just, yeah, sure, no problem. Okay, thank you so much. Thank you. Oh, no problem. I'll get back to you in just a moment. So all you have to check, okay, let me again, you might be wondering, should your compiler do the proof? No, don't do it. It's not possible, right? So again, your compiler, okay, This is your compiler. Okay, some input programming language on your own. And then that one there is going to generate some output, which is at the same time the input, let's say for PVS, for example, right? Some tool. Okay. So now, first of all, as long as this particular output can be loaded, which means it's type correct, right? Can be loaded. Consider as valid. Can be loaded. That's a good start, okay? Exactly how you prove in the tool, if you can show it to us, that'll be very good, okay? I would say it's not required to prove that the output is valid. If you can't, okay, negative, if you cannot find the proof. So I don't want you to waste too much time just proving things, in the PVS tool, for example, right? That's out of the context. As long as you can generate something that can be loaded and also the generation process is kind of convincing that it's actually correct, then we are happy, okay? All right. Of course, it will be nice learning outcome for you, for your personal learning outcome, if you can interact with the prover and demonstrate to us, okay? I'll be more precise a little later, okay? I'll write it down, okay? Any questions you want to ask? You're fine, right? Okay, oh, I thought you got a question. Okay, you want to finish the final bit, and then we have to make it.
Okay, so we are, there's only 4 demos. We have done all the proofs, and then we can exit the PVS. It shows, yeah. And then we can run a command. I'll first get the command first. That's it. How do I select it? Control C, Shift C. Can I prove? Can I paste? Okay. How do I copy? Jackie, Control C. Command C.
Command C is back.
Of course, Command C. Of course. I hate typing. Okay, that's good. Okay, so we can run this command to show the proof summary. It's gonna take a bit. Then there will be a summary file. See top.summary, and then we can cat it. Top.summary, and then it will show that we have done all the proofs. That's it. Thank you. Thank you.
Thanks so much. Yeah. Thank you, Shangru. Thank you. Yeah. Guys, any question in general? Just okay. Just get some idea. So, however, I will give you a personal tip. PVS, unless you spend so much time with it, the interface may not be so easy to use. Okay. But he took a course, so that's why he got some advantage. But that's okay. In that sense, the COQ, the COQ Theorem Prover, might be easier to use. I'll give you a little personal advice. Might be easier. Okay. All right. So now the plan would be I'll take just another 5 to 10 minutes. I'll finish 1 slides, and then we are done. How about that? Okay. Do you have any more questions related to the projects? You can now feel free to ask, since we are now diving into it. You okay? How many of you already hopefully started looking at the tool, right? How many of you who have not? Okay, guys, you should, okay? It's a friendly reminder, okay? Friendly reminder. You really want to start, okay? Okay, just 1 slide, okay? Today, we wouldn't go anything about algorithm. I'll use a big chunk of time next time to actually finish that properly. Now, we already finished the topic about top-down parsing, okay, top-down. And the next one will be bottom-up parsing, which goes in an opposite fashion. And what we want to do eventually to learn is, rather than trying to find out the leftmost derivation automatically, like in the top-down parsing, now we are trying to do rightmost derivation. But why, right? This is an interesting part about it. I'll give you some intuition today, abstractly, okay? And then the idea would be I'll try to spend only 2 more lectures on finishing up all the parsing stuff. And then for the remaining of the course, we'll try to finish other things, optimization, semantic analysis, etc. That'll be the plan. Okay. Okay, let me just go over some points with you, and then we'll do the technical part on Monday. Okay, hopefully 2 lectures. Okay, there's a reminder for top-down parsing. We built from the start variable, it's a starter node, right? The root of the tree, and then try to expand. You pretty much know the process. And it's important to realize it's the leftmost derivation, right? We start from the left, right? Always. And now in the bottom-up parsing, I want to just go over some idea with you quickly. What we're doing is, for the scanner, we are still going to get the words from left to right. So what I will do is I'll give you some abstract example quickly, just to draw some conceptual map. Okay, I will put my notes here. Okay. So now you can think about the scanner is going to have a sequence of words over here that's going to be returned back to you. Let's say in total we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's say we got 9 different words. And then you can assume there's also some EOF at the end. Okay, let's say. And the scanner is going to go from left to right and go one word at a time and give back to us. So for that part, it's the same. Okay. Eventually, we're going to say the the bottom-up parser that we are considering, they're also called LR1 parser. And notice the contrast as opposed to LL1. Quick question: what's LL1 stand for? Go ahead. Left to right. Left to right, leftmost, and one look ahead. Yes, just left to right. Don't forget. Okay. And then over here, hopefully it's not too difficult for you to guess. Left to right, rightmost derivation with one look ahead. Okay. So now the critical difference is the rightmost derivation. We're going to see that in precisely on Monday. But okay. So now the first point is the word will still be returned back to the parser for processing left to right, and then now. The most important concept for bottom-up parsing is about reduction. Basically, go backwards. Okay. So what I meant was, for if somehow, let's say we got alpha and beta, for example, over here, and if in my grammar there is something called A produces alpha beta, for example, in that case I can just reduce them into A. You can see we're going bottom-up. Okay. We're going to focus on some concrete example on Monday, but as long as you get this fundamental step straight, everything else is not too bad. Okay, and then I'll give you another intuition in just a moment. And then after this, okay, and then reducible simply means you can find out the right-hand side of the production rule matches the string, and then you want to reduce to the left-hand side, basically. Okay, and then you will keep doing this kind of reduction until. Can you take a guess? Until we get to the root, which is the start, exactly. So you want to keep doing until, I'll give you one example. Let's say maybe I got, for example, A here, and then maybe somehow I got another one called B, and then combining B, AB, and also this next one, I got C. Don't worry too much about, you may be wondering about precedence of your grammar, but don't worry about just yet. We'll see the algorithm on Monday. And then maybe this guy over here, it will be D, and then combining C and D together, we actually got this guy here, we got E. And E, let's say, is a star symbol. And then eventually, that's kind of the parser we can build, bottom up. Okay? So far, so good? It's only to get intuition. Question, Abdul. Good question. So in this case, apparently, okay, let's see in this case. You can see we already reduced to this particular star symbol. We have reduced to this symbol here, and then we have consumed all the input words. So that means it should be accept. That's easy, right? So what can be the possible cases for reject, to say syntax error? Basically, think about, we'll see more precisely on Monday. If somehow you're trying to do reduction there, but somehow you just couldn't get to the star symbol, there's no such reduction will lead you there, even after backtracking. In that case, it should be a failure. We'll see precisely how that can happen. Okay? My only concern now is if you can, based on this particular intuition, okay, can anybody try to tell me the answer for this question? I got accept, I got reject, right? Here's a question. And then once we're done, we're done. Okay? I'll read it out to you. Why can the bottom-up parsing find the rightmost derivation, if any? Why? Why? Based on what I said over here abstractly. Why rightmost? So based on this, you can see, okay, let me be precise again. You can see the way I do for this abstract example, I would say this particular guy, oh, let me use a different color, okay? You can see these two guys, I will reduce them to A. And then these two guys are reduced to B. And then these three guys are reduced to C. And then these three guys are reduced to D. And then these three guys over here are reduced to E, right? There's certain order I'm following. But why we can claim theoretically, if you actually find a successful case for bottom-up parsing, at the same time you also find rightmost derivation. Can anybody tell me why? Using what I'm using here. Go ahead, she.
Because the rightmost ones are the last ones that so,
Okay, that's on the right track. Abdu.
because if you base it from the up, then you keep going all the way to the right.
Uh-huh.
Then all you have is the rightmost.
Pretty much. Ashkan, any input? Okay, that's fine. Okay, so basically what we're saying is, thinking this way. If I try to do some tracing, let's say when we talk about in terms of the parse or reduction, the order in which I did it was A first, right? And then followed by B, followed by C, and followed by D, and followed by E, right? So now, given that we got this complete parse tree, assuming that it's successful, what would be the corresponding rightmost derivation? Yeah, since we say rightmost derivations, right? So E should follow B, and then go to C, and then go to B, and go to A, right? Okay, so now let me write it down. The corresponding rightmost derivation should go like E, D, C, B, and A. And what's the relationship between these two sequences? Reverse, okay? That's a very important insight to get. So why people claim by doing a bottom-up parsing, eventually you already find the rightmost derivation. Not directly, but in the reverse order. You can just reverse it eventually. That's all the intuition I want you to get today. Mahu? I would say just different flavor of doing it. Yeah, but for example, what I mentioned for Antelope 4, they actually generate an LL parser, which will do top-down parsing. But I believe there are other parser generators. I'll look it up and tell you maybe on Monday. So there are other parser generators still generate parser doing bottom-up. Yeah, we'll talk a little bit more about implementation. Guys, any questions?
So what's the advantage using bottom-up over?
I would say theoretically speaking, they are just building a parse tree. Either go for leftmost fashion or rightmost fashion. So it doesn't matter. Your goal is really to determine if the input string is really valid for your grammar. And you're trying to find a parse tree for that. Yeah. Okay, any questions? Okay, if no objection, can we call it a day here? Okay, I'll see you next week. All right.